let's begin. We were talking about the NC class, and although we will discuss a little bit about binary search, I was going to bring it up when we talk about parallel algorithm or parallel program design later on also. But let's spend just a couple of moments. I want to search in parallel. Okay, forget about binary search. And so, although binary search is the context in the background, which is what we start with by saying that something can search through sorted lists in log n time, can we do better using a polynomial number of processors? And one of the things that you might remember was I said that you want to make as big sequential sections as you like, as you can, and then try to postpone the synchronization for later. Right? So I would say a great way to do this would be I take n processors, I give everybody a length 1 part of my array, right? How long will it take to search? Order 1. So, is it parallelizable?
So if you find it, then you write your address in this location and the priority.
So yeah, so it can be agreed. It can be done in order 1. As a matter of fact, we didn't actually do any binary search at all, right? You might as well have had the array completely unsorted, and I would still be able to find it in order 1. But how much work did I do? Order n, right? Which means now that I implement it on a P processor machine, I expect to take how long? N by P, right? And that's not comparable to log n.
Like you implement binary search in that, then it will maybe.
Well, so that's what we were trying to do. We're trying to do binary search, except in binary search we said we have n processors, we'll give everybody a sequence of length 1. It is binary search, right? It just degenerated into regular search, into sequential search. And so speed up over that was good, except the work done was too much.
But why would the time taken be n by p if you have like p processors? Is that the time taken or what?
The time taken.
So if you have a binary search algorithm and p...
No, that same algorithm. The algorithm is that everybody checks if they have the element, and if they have it, they raise their hand, right? Somehow they say that we've got it. So that specific algorithm, which can now be implemented using work scheduling principle on P processor machine, will take n over P time, because the work done is order n. So we would like someone to do less than order n work. It doesn't matter how many processors you begin with.
So this n over p is for sequential, not binary.
N over P is the time taken on a P processor machine for the order 1 algorithm.
What if we have the binary search algorithm but only for one element, which is kind of useless, but that's the algorithm. So it's not a simple equality check, we do the exact, we have a low, mid, high.
Okay, all right. So now I said everybody take 1 over P of the original list. You've got it sorted. And now you take log n time, log n over P time, right? If that is your algorithm, how long does it take overall?
P times.
Log of n over P.
What we do? We give each of the processor 1 by p of
Yeah, so that's what we did. We said instead of searching through that the way the original algorithm would have been doing, Now you do binary search in your share of n over p elements, and that you can do in log of n over p, and one of them will have found it, it will raise its hand. Can you do better? Yeah, so yeah, I missed that part. How much is the work done? P times log of n over p, right? Because everybody was doing all the work all the time. Can you do better than that? Actually, maybe the work directly doesn't make much sense in this context also, because we've already gone to NP processors, right? So it doesn't add too much to the discussion.
Why is it bad? Got log n.
We would have got pretty close to log n anyway, right? Log n is the binary search time, and we have said instead of log n, we have turned it into log n over p. Can we? Yeah. So that's something that you would consider an improvement, right? Asymptotic improvement. Something that was polynomial can turn into polylog. That's a parallelizable algorithm. Similarly, if something is log already, can you turn it into sublog? Another alternative might be that you instead of saying you take 1pth of it and do binary search in it, because very quickly you'll know you don't have it, right? So when you do this binary search, one of them has it, you don't have it, so you'll know immediately that it's not in your range, and then you're sitting idle. Right? And that one guy who has it is going to take all the time. So that's not a great load balancing.
So we can keep dividing the array into like p parts. So like you know that one part has it, and so then the other people, the processors, can divide that part into like p different parts, and then searching those and keep doing that recursively.
Okay, so the algorithm now is that you take the array, and instead of checking if the element you're looking for is the right of the middle or left of the middle, you divide it into n chunks, p being the number of processors, and you decide, the first processor decides if it is the left of the n over p position or right of it. The second decides if it is less than n over twice of that or right of it. And so you've got p different places where this test is being done. In order one time, everybody has done one test. And how do we know?
Everybody raises one.
That's right. If you
I can't understand everybody.
So whenever there's either, if all is left, then you know it's in the first part. Similarly, if all is right, then the last part.
Who knows that all is left?
Means we have to maintain a global array.
But who's going to check that global array?
For example, in group and MP, then the master can take over and
Then the master will take n time to find out.
No. So if I see it is within my right.
Wait.
If I see that it is to right of left, and to left of right, I say I have it. So there is a common memory block where I put in my processor ID.
Right. So it's not simply that I'm checking whether it's to my left or my right. I'm saying, is it in my range? Right? You can do it by doing two tests. You can also do it by doing one test and then checking what your left neighbor found. Right?
That will be sequential because
Everybody does their test and checks the left neighbor's test. Why is it sequential? And only one will know that their test and left neighbor's test were different.
There are going to be two comparisons, right?
There are two comparisons, either way. Huh?
2 is okay.
2 is fine, right? So in one case, the comparison is whatever the search comparison is, which is expected to be heavy duty. In the other case, you are looking at the results of your neighbor. But still there is a 2 comparison thing.
This is still a log n time algorithm, though. The base is different, log p.
Exactly. So now how much time does it take? Now everybody has to know that guy determined it. Right? So there's one location where somebody has written the left range is not 0 anymore, it is this L1. Right range is not n minus 1 anymore, it is L2. And then everybody does a subdivision of L1 and L2.
N by p square.
The gap L1, not p square.
N to the base. I mean the number of
So yes, you're going from n to n over p to n over p squared, right? So when do you get to 1? Log of n to the base p, which is same thing, right? Log n over log p. And the earlier algorithm, which did a lot of wasted work, how much did that do? Log n minus log p, right? Log of n divided by p. So it went down a little bit. It had a lot of wasted work. Now we are not wasting any work. Right? Everybody is busy all the time. You went down a factor now, right? But still a factor of a constant. Okay. And how much work is done here? Again, it's p processors doing over certain number of time, right? So p times log n over p, over log p, which is more than log n. Right? The thing is that you are now doing asymptotically correct amount of work. Right? Log n is the time spent by the serial algorithm, and you can't do less work than that. If you can do less work than the serial algorithm, then you found a faster serial algorithm, right? So the amount of work done by a parallel algorithm has to be greater than equal to the amount done by the serial algorithm. So if you're doing log n amount of work, then you know that you can't asymptotically get better in terms of work. But even with that kind of work, your time is, at least so far, high. Okay. Let's get on.
So is it a better algorithm than what we talked about?
No. So there is the same notion of NP hardness and NP completeness, except whatever was NP in the sequential domain is P now in the primal domain, right? In the parallel domain. And so, except the notion of reduction is also slightly changed. Whatever was NP has turned into P, and whatever was P has turned into NC, and what was polynomially time reducible has turned into NC reducible, right? And reducible in parallel in using a polylog number of steps. Okay, so just let's look at these definitions very quickly. And they will be up on the slide, so you can go through them also. This is more so you understand the concepts and understand the kind of the landscape in terms of what are somewhat hard problems from the point of view of parallel programming and some not so hard problems. So we say that language, and this is now determined in formal languages or written in formal languages terms. There is also a functional variant of all of this, but we simply say, think of it as a decidable problem, right? Well, we have a question, language L1, and we want to know if the language L1, or deciding if something belongs to language L1. If L1 belongs to P, that means effectively, we are saying that there is a problem that can be solved in polynomial time. That language recognition problem, right? Right now we are basically defining everything not in terms of taking a problem and solving it, but having an equivalent language and asking if an element belongs to this language or not, recognizing this language. And so we say L1 belongs to P is NC reducible to another language L2, which also is a polynomial language, right? Which means its recognition can be done in polynomial time. Then we use this notation that L1 is less than equal to sub NC L2. If there is such a function f that we can map from L1 to L2, right? If you give me an element in L1, I can apply f and get an element in L2. And the computation of this f, getting the element in L2, is efficient, parallelly efficient. It's in NC. If I can compute this efficiently and I can recognize L2 efficiently, that means I can recognize L1 efficiently. Because if I don't know how to recognize L1, I know how to recognize L2. I know how to map a problem from L1 to L2. And so I simply map the problem and call this subroutine to answer that question. Okay?
Does that depend only if it that? Is it the other way around also?
No. It's one way. Other way around means something else. In fact, if L1 is reducible, NC reducible to L2, that means that L2 belonging to NC implies that L1 belongs to NC. That means if L2 is known to be fast, parallelizable, then we have just shown that L1 is also parallelizable. And vice versa also, right? Meaning that if L1 is not in NC, L1 is known to be inherently sequential, then L2 will also be inherently sequential. It's the same thing. A implies B means if A, then B has to happen, but if not B, then not A also has to happen. And a problem L, again a language, L is P hard. If you can take any other language, L prime, which can be reduced, NC reduced to this L, for every L prime that is in P, whether or not that is efficient. Okay? So it's very similar. It's basically the same definition as NP hard. Reducible has become NC reducible instead of polynomial time reducible, and you replace P with NP everywhere. Okay?
What do you call P-hard problem?
P-hard problem is something that we expect, we think, are not efficiently parallelizable.
Right? This notion is different from the sequential.
Where NP hard has the same connotation. The definition of NP hard is the same. NP hard says, and a language L will be NP hard if you can reduce other languages L prime to it in polynomial time for every other language which is known to be in NP. And then in NP hard there is a subset that we call NP complete. Similarly in P hard there will be a subset called NP P complete where they map to each other. Okay? They can reduce to each other. So this is just to give you an idea that the same things apply, but this is the main point of all of that discussion, is to look at a couple of problems that are not known to be in NC. These don't, as of now, have an efficient parallel algorithm, and we don't expect, right? Just like we expect P is not equal to NP, we also expect that P is not equal to NC either. So circuit value problem, which is simply, I've got a bunch of inputs, I've got a bunch of gates, and you tell me the output, and I will tell you whether or not that set of inputs, given these, going through these gates, produce 0 at that output or not. Linear programming is another. It can be done quite efficiently in sequential, right? Order n, linear time. And so it's not even in that class of already logarithmic like binary search. Okay, it can be done quite efficiently in sequential time, not efficiently enough from NC's point of view, but still you cannot reduce it to logarithmic polylog time solution. And linear programming basically says that I've got a bunch of constraints, planar constraints in any dimension B, and I want to make sure that a point is on the positive or negative half space of each of those planes. Okay, and that's a feasibility version, feasibility problem version, and the full linear programming version is a minimization or maximization of some objective function within that constraints. Okay, so it's just formally written down in that fashion. Compiler type stuff, not easily parallelizable. Checking if some input belongs to a given context-free grammar, for example, cannot be solved efficiently in parallel. From geometry, checking if some point lies on convex hull cannot be done efficiently in parallel. Right? Convex hull is a set of the points such that their convex combination is well, that's a vacuous statement. Convex hull, of course, has a convex combination. Convex hull of a set of points is the set such that any line connecting any 2 points on the hull remains inside that hull, inside that convex hull.
Problems, do we observe some common obstruction which stops them from being?
They're all different types of obstructions, and at a high level, you can say that there are inherently sequential parts to it. Right? For example, and all of them have that thing that you have to depend on something else to get to this the next step. And so there are so many dependencies on these number of steps that ultimately you cannot do this in log n time.
And this can be LP problem. So given a point, I need to say whether it is in the feasible region for all inequalities.
No. LP, that would be very efficient, in fact.
Right. So what is the problem?
The problem is that I've got a bunch of planes. All right. The feasibility version of the problem only says I've got a bunch of planes. Does there exist any point which is in the positive half space of all of the planes, or negative half space? That's another version. The full linear programming says that I want an objective function given the set of x, y, z, w, whatever, however many coordinates I have, some linear combination of those objective functions, and I want to know where in this feasible space is this objective function maximized. Okay, that's as much as we are going to talk about complexity and parallel computation models. I'm going to switch to memory consistency models and then on to programming design paradigms. Any questions on stuff we have discussed so far?
So the problems of reductions and in the prefix sums and all. So those problems are also perhaps not in NC.
Not in?
NC.
Not in NC. They can be done in log n time. So why do you say not NC? Because binary search is NC. Binary search itself, although we realize that when it is NC, that doesn't always mean very much for all problems.
Perhaps I will ask it wrong. So it is log n time, but we cannot get much efficient parallel algorithm as compared to the existing sequential.
String sequential one? Existing sequential ones.
Yeah. What I want to say.
The sequential is order n, right? N steps.
And in parallel, we can do it
in log n time. Prefix sum or we'll do those things. So we'll go through standard parallel algorithms that you'll use as subroutines in a variety of problems, but we'll get to that in maybe a month from now, or maybe less. Okay. Any other question?
So whatever is NP is still NP.
NP is still NP.
You said whatever is NP becomes.
No, I was just drawing an analogy that every definition that you would have seen in NP, just you replace some keywords and you've got this new set of definitions. And you all probably already know this. This is getting almost truncated at the bottom. The notion of cache coherence, right? It's basically at the hardware level, typically implemented. We've already discussed this in short before also. There are a number of processors. Each, in this case, they are written as T1, T2, etc. They are threads, so to speak. They may or may not be running on the same processor. And they have their local data stores, maybe caches. And then there's some shared data store, the green colored one, which is the shared memory. And you're going to read and write, and everything is just going to stay in the cache until it needs to be evicted, right? And so you write something to the cache, the other processor writes something to its cache, and you read something back after that other processor writes, you still get your data back. Okay, so you don't want that happening, and that's why cache coherence is built into hardware implementations. And any honest to goodness machine will have some level of cache coherence. And that essentially means keeping the cache state consistent. It's another way of saying that you basically hide the cache from the program. The program shouldn't have to know that the data came from cache. It should appear to the program that the data came from the shared memory, the main memory. Okay. This is typically going to be implemented using the invalidate type protocols that we saw. So there's dirty bits and all that maintained. So this is an example that you would also potentially have some Snoopy cache, which is a little bit more efficient, but much more hardware required, where you keep figuring out what cache information is flowing on the bus to update yourself without somebody having to tell you that that other fellow has written a new information in that data item. So we are going to take all of this for granted, right?
When does cache data flow on the bus? Because if you update your local cache,
it depends on write back and write through policies. Right? So Snoopy cache will only work when you write to cache as well as into the main memory. All of this is typically at the granularity of one cache line. So if you see a cache line going on the bus that you also have, you're going to update your cache line because that cache data being written is more recent than yours. Okay. So the context is one memory item, typically a cache line. It may even be 1 byte, 4 bytes, whatever. So it depends on the architecture, but we'll just say a cache line. And that is from the hardware's point of view. Okay, so this is the hardware-centric view. What we need from the program's point of view, right? We're writing a program and we say, okay, the hardware makes sure that there is cache coherence, meaning that if I write X, then the other processor will know that value of X. Okay, if that guy also has it in cache. If that guy doesn't have it in cache, it doesn't care, right? It's not going to look for that X. Is that enough? Is that sufficient? Or do we need a more global view? Okay. The entire memory's state needs to be somehow consistent. Meaning that, sorry?
As in, anything that's changed.
As in a variable x and a variable y at a completely different location may depend on each other. Pointer is one possibility. The other is just pure logic, right? I've read x before. I don't have it anymore. But I have used that in y, in computation of y. And so from hardware's point of view, it's just matching addresses. But from program's point of view, it's the overall state of the program.
No, but that is like, I mean, so the hardware can give you this, that if it got it done in this cycle, from the next cycle onward, it will be accessible from the new value in our processes.
Yes.
You would expect that in a variant in the
That is enough. That is that's I should say that's all that the hardware is going to provide. That's not enough from the program's point of view, because you are not even going to read that. You're never intending to read that guy's written value.
Because you read it before that.
Because you might have read before that, long time back.
So then it is a synchronization that the programmer should be.
Right. So that overall consistency has to involve the programmer over there in that paradigm, where the only thing that the hardware provides is address-to-address coherence into the cache, and then the programmer takes care of all race conditions. That's one model. The other is that the underlying system gives you a better view of consistency, a better consistency of memory. Okay. And so in this case, the context is the entire memory, and we want somehow your programming interface, the compiler, the hardware together giving you this view. Right? A contract to the programmer that says that when you access things in that way, this much is guaranteed to happen. And these kinds of things are very easy to do in a uniprocessor domain. So there's only one fellow interested in anything, and whatever may be along the way can all be reordered in the same way so that you get everything pipelined in the same fashion. Okay. But as soon as you have got multiple processors, even if they are talking to the same shared memory, there is typically difference in the timings at the level of the logic. And sometimes they may not actually physically be a shared memory. Right? Sometimes you may implement shared memory on top of some distributed memory network. And so in that case, it's very clear that latency for some writes is going to be much higher than for some other writes. Okay, so it's easily going to get reordered by the system. And you need to make sure that when the program logic is seen, some consistency that is expected by a programmer is provided. Okay, so to look at some of these definitions of consistency.
So in that case, for example, some writes may be frivolous. So what is the point in keeping those writes just to? If the compiler can make some betterments or time savings by removing such things.
It might be able to do that, but first we have to determine what the contract is that the compiler is making with the program or the programmer, right? In a uniprocessor domain, it makes a lot of sense. I write something, I write it again, you get rid of the second one. But when I write two things, one after the other, somebody else may read the state in the middle, and I can't simply say, oh, I don't worry about this at all. Okay. So when other programs may be, it may or may not be the same program running elsewhere, right? It may be a completely different program accessing the same piece of memory.
Alright,
So you have
not compile them all at a time.
yeah, you have no idea how that is going to behave. Okay. And so the most stringent model of consistency, memory consistency, is called the strict consistency model, where you basically have a global clock, and anytime somebody says read, everybody stops doing everything else, that read gets completed, then they start effectively. Right? Means everything happens instantaneously.
Who's giving this? I mean, to whom are these consistency definitions applicable?
The consistency definition is simply a contract with the programmer, which means that the underlying this hardware software thing that the program is sitting on top of is giving you this behavior, is giving you that apparent behavior. How it's managing underneath is its business.
So each one gives its own set of read and writes. How the underlying hardware behaves for this, what he expects and what the hardware does. Is that what it says?
No, this says what kinds of different things. So there are two parties to a contract, any contract, right? The programmer and whoever is providing it. In this case, the hardware compiler together. And we are trying to understand what the program wants to see. Okay? And then see whether that's what the hardware wants to provide. Okay? And balance it out. And strict consistency is what a programmer would like to see. So everything is globally ordered, so I know when I am reading that other guy's read happened 5 milliseconds earlier, and so it happened before me. No race conditions. No race conditions, because I know the timings.
So two things cannot happen at the same instant.
Same instant is not allowed. Right? The hardware is going to somehow order everything.
Two things can happen, but the programmer aware that how is that going to happen. That's not like
So the memory
No.
are all sequential.
Everything is done instantly, and there is this additional kind of hidden rule that instantly may not be the same instant for two operations.
Right, but as a computation, they may happen at the same instant. It is the memory access which is the only thing which.
So the effectively, right? So the program is going to see some behavior from the memory. When it reads, it sees something. Basically, that's the response that it gets. When it reads something, what is the value it's going to get? Right? And so there is a read and there is a write, and you were not going to allow them to happen instantly at the same time. Each will happen instantly, but one has to happen before the other. That's the strict consistency model.
The order is deterministic. The programmer knows what the order is.
Those details are not necessarily part of the memory consistency model. It just says that when I make something at a given instant of time, right, we all know the time, and that guy makes some other request at a given instant of time, and we cannot make requests at the exact same instant of time, then whoever made it earlier is going to go earlier. Is going to start and finish before the other one starts. Okay, it's atomic.
What is the benefit of this to the programmer? Why does a programmer want to see this?
Because everything is atomic.
Yeah, the order is still unknown.
Order is given.
Conditions, right?
No, order is known because you have the clock. Right? Everybody knows the clock. So you can see what time you have made this request. Okay.
How do you program in such a model? So as you pointed out, if I have two threads which have to read and write text, so how do we synchronize?
There is no actual implementation of this model.
Now suppose there was an implementation, how do we use that implementation?
You would use that implementation by knowing that I have made this request at a certain instant of time.
As per my code that I have written.
Yes.
These many instructions before it. So this is the
Yeah.
24th instruction.
24th instruction, and that guy, and I can write even the instruction number where I'm making this access, read or write, and then I'll know whether that guy got it first or got it later.
But it's still non-deterministic.
You can make it non-deterministic, but you can also make it deterministic given this model. Okay.
Because you can have checks on the.
You can have checks on the timestamp. Everybody has access to this timestamp.
Every step's timestamp.
So every step is timestamped. Exactly.
Two things happen at the same time. What does it happen? That's what.
They are, so you can think of, so again, you're probably too worried about the implementation part of it. The issue is of, and in fact, that may be one of the reasons why nobody implements it, because it's extremely challenging to perform. In fact, just providing a global clock is next to impossible. Okay, in a distributed setting, especially. But you can simply say that I've got timestamps by steps, and your processor number is now sub timestamp. So you will always go first, you'll always go second, you'll always go third, you'll always go fourth. So now everything is disambiguated. So that is one way of doing it. Okay. But there are many others, and who knows what different contexts might prefer. A slightly weaker form of this strict consistency is, again, it appears atomic, but that global timestamp is only approximate, vague, right? Meaning that I do something here, I do something else over here, and between these two times, accesses, right? I do an access over here some time later, and there is some timestamp for this which is definitely more than this, and my access, this entire thing, is going to get effectively, right, what is going to be visible to all the program, right, the system as a whole, will effectively get done at some point of time, atomically. But based on this approximate timestamp. Okay, so we are not in lockstep fashion. We don't know exact timestamp at any time, but we can't be off by too much, because next access has to have a bigger timestamp.
Is it possible to take an example?
We will take some examples.
Still there's a global clock.
There is, so basically we'll take examples of especially the ones that we will use. The global clock is based on the original statements of the authors. Basically says the global clock is not required to be fully synchronized. Okay, what that means is that we don't know the exact time when the process said, I want to do this.
We can still order them.
We can order them in all the models, even the weaker models. But we are going to somehow order them not just based on their relative position in the program, but with respect to a loosely synchronized clock. We don't have to know the precise time at which so this is somewhat similar to one giving you a fully deterministic sequence, one giving you somewhat non-deterministic sequence, except it still is atomic. Okay, so every access appears to happen instantaneously, but at what time it appears to happen instantaneously is can vary by a small amount, right? There's some delta lack of synchronization that they are going to allow. Okay, so those are impractical models. primarily because of the expense in implementing this synchronization. If both of them expect some notion of this global time. I need to be able to know that the time is so many units. All right, and they have generally been used to prove theorems about solvability of some program, of some problem, and the like, right? Or lower bounds on certain things. But you will see that the actual consistency models provided by real implementations are much, much, much looser than either of these. And the primary thing that goes first is the clock, notion of clock. So this is probably the first relevant, still the strictest consistency model, which is called the sequential consistency. All right, and was first given by Leslie Lamport in 1979. And it says that, and this is, I think, something we discussed shortly earlier also, briefly. Says that in a multiprocessor system, when there are many processors talking to the memory, the interface or the programming paradigm is sequentially consistent if it is equivalent to some linear ordering of operations. Okay, but that linear ordering must respect the ordering of each individual program, right? You take the subset of so all the operations are going to be ordered, and as long as that order can be generated, it is sequentially consistent. But you take the subset of that set of operations for each thread or processor, or what originally it said processor, then it's going to be the same as that processor's requests, accesses.
So you can interleave them.
You cannot reverse them, right? No, you don't interleave them still. It's not that you say that read has started here and ended here, because that's the original completely concurrent model, where I don't know when it is going to finish. I give read here, and at some point read has happened, and that overlaps with lots of other reads and writes. If you do that, then everything has to be dictated by locks and the like. Okay, so that is a full concurrent model. Here, in sequentially consistent model, it is the behavior that a program sees must be the same as the behavior seen by some sequential program, given that order that this overall system saw, seen by that sequential program, right? Meaning that if I sorry, so it's effectively providing atomicity
to each line of code that are
to each access, right? So each read or write separately.
So I was actually talking about the accesses being interleaved from different processes.
They will be interleaved in reality, right? But it should be effectively, right? I'll get to an example right now.
How is this different from the weaker consistency model which we discussed in the previous slide? And that's also in
Previous slide, or when we are talking about OpenMP.
those are MP. We just discussed the strict one.
Yes.
So it had a weaker.
Which had a notion of a loosely synchronized clock. Here there is no notion of clock.
So, but
The ordering can be ordered anywhere, right? So you're basically saying I've got these things here, these things here, these things here. Just merge them in any fashion I like.
You just take the results of what happens and you remove a subset of one particular processor, the program order should be maintained. So that's what it teaches.
If you take one processor's accesses, then they have to be ordered in this global order.
Its own program.
Its own program.
So let me restate. You create a global order. all accesses are there in this global order, all reads and writes. Okay. Now you only consider the accesses made by thread 1. In this global order, they must appear in the same order in which thread 1 made them. Okay. That's all that's needed. It seems reasonable. Turns out to still be hard to implement. And it is its performance, wherever it is implemented, its performance is not that great.
Because of the atomicity of every x.
Yes. So here is an example. I've got two data items. Ready is 0, data is 0 when we begin, right? And two threads have started, thread 1 and thread 2. And thread 1 says data is equal to 1 and then ready equal to 1. And thread 2 meanwhile is reading ready many times as long as it remains 0. Right? As soon as it sees it's 1, it comes out. And it comes out and wait, that's not supposed to be indented like that. There's a semicolon, yeah. It keeps looping.
So the tab is actually.
Yeah. So the tab is extra. And then it sets private equal to data. Right? So when it thinks that the data is ready, it makes a copy of it. Okay. So what are we expecting in terms of sequential consistency?
Then you will be trying one only of data will.
Basically, it means that if you have seen ready's value, data must be before it, because in its order, data has happened before it. So the program expects that when I have seen that ready is 1, I'm guaranteed that data is also 1. Okay. I don't care when data got written. I don't care when my access came in, my read values came in. I don't know if a given read for the ready and a given write for ready were ordered in a certain fashion when it was looping. I don't care about that. But if I was doing strict consistency, there has to be an order among all of them. Okay? All those reads have to be done at the time that the global clock said that it's supposed to be done. Here we don't care. You can take all my reads and order them after the data has been written, before the data has been written, or after the ready has been written. Okay? I don't care when you did it. You can order it anywhere. Okay. So here is a little table that shows that if T2 reads 0, then data might be 1 or 0. If T2 reads 1, data is definitely 1. Okay, here is another example. Oh, wait, what happened? It's a little slow. On my laptop at least. So I've got 4 threads. Thread 1 writes the value A to variable x, address x. Thread 2 writes B. I don't know anything about atomic clock, global clock, right? So I don't know whether x equal to A happened first or x equal to B happened first. If I was asking for strict consistency, I would know which has to go first. Okay?
So we enforce that using that rule.
Previous one? No, we were not enforcing anything. In the previous case, that's what the model was providing to us. We were expecting that if you have, so let me go back to the previous case. We were expecting that if we are reading ready equal to 1, by that time data must be valid because I am now going to read data.
So it's sequentially consistent is implemented, then you are ensuring private will be.
Then you are expecting this program to behave correctly. Okay. If it is not sequentially consistent, then it may behave erratically because data and ready may be done in a different order. It's possible that data is far away and writing to data takes longer than writing to ready. Right? So ready got done, data never got done. In this case,
Why was the previous model?
yeah. That's where I'm going. Thread 1 wrote the value A into variable X. Thread 2 wrote the variable B into X. Thread 3 is going to read, okay, X twice. And thread 4 is also going to read X twice. Okay. And the bracket shows what the value it got when it read. Thread 3 read B the first time and A the second time. Thread 4 read A the first time but B the second time. Because maybe thread A had was closer to B, closer to the second write or whatever. Okay. Now any order you produce can't provide what they saw. Okay. So that means there is no ordering which is consistent with the responses that everybody got.
The model that was used to implement this kind of behavior is not
sequentially consistent if they saw this behavior. Okay. It turns out, as I said, and I'm going to stop now because we're running out of time. Sequentially consistent is meaningful. You can write programs with a lot of guarantees on when races will not happen, but it's surprisingly hard to implement, and nobody does it either. Which means that we'll be looking at even more lax models of consistency, which OpenMP, for example, implements something that we said is weaker consistency model. It is something called weak, and it is weak than the weaker. And there are even less strong consistency models that actual multiprocessor implementations use, okay, in which case basically they are shifting more and more responsibility to the programmer to make sure that all of the race conditions are either avoided or controlled at the cost of giving better performance. The idea is that the programmer knows best of where the race is likely to occur. But it's the same story. There's enough rope to be given, you can use it to tie others or hang yourself. Okay? All right, so we'll stop here now.